Hello, and welcome to today's webinar on adding static code analysis to your CI/CD pipeline. I'm Christina Cardoza, news editor of SD Times. Before we get started, I have just a couple of quick housekeeping announcements. First, this webinar will be recorded and available on demand through the sdtimes.com website in about 24 hours after the event. Secondly, if at any time you have any questions about or during the presentation, you may submit them using the Control Panel's Questions tab. Here at SD Times, we've been covering the pressure development teams are under to release code faster. The problem is that making sure that code is safe, secure, reliable, and of high quality is time-consuming. With static code analysis, teams can detect and address any problems earlier in the lifecycle and improve developer efficiency. Today's webinar will go over why it is essential to pair static code analysis with efficient software development practices and how to add static analysis to your DevOps process. Here to discuss this further, we have Stuart Foster, Product Manager of Klocwork at Perforce Software, and Steve Howard, SCA Specialist and Technical Service Lead at Perforce. Now to get things started, I'll throw it over to you, Stuart.
Thanks, Christina. So today we're just going to go over a couple topics. Why embedded code needs to be safe, secure, reliable, and high quality. What are the requirements and costs of achieving that? What are continuous integration and continuous delivery pipelines, how CI/CD pipelines improve efficiency, and how CI/CD pipelines can be enhanced with static analysis. So, why is it essential code is safe, secure, reliable, and high quality? Well, the world is run on embedded software, quite frankly. Every day there are more and more connected devices. We have our Internet of Things and smart devices everywhere. As we connect devices, both old and new, and having safe and secure code is becoming more important. Historically, non-connected devices didn't necessarily follow secure standing coding practices. It was more of a secondary consideration. Really, at that point in time to market was key. So what are the conflicting needs for software to be safe and secure? What does it cost? Size is a problem. For example, cars, they used to be simpler, having only a few ECU controllers, and they were running, thousands of lines of code. Now they're effectively rolling computers with hundreds of million lines of code, more than 50 ECUs, all connected and talking to one another. The future size of these code bases are just going to continue to grow extremely fast and becoming more and more complex. And there's an emerging need for the connected vehicle.
And there's also a problem with complexity, Stuart. We've seen, in recent times that even going back a number of years now with the issues they had with the Toyota electronic control, throttle control system. Once they looked at that and the problems that caused a lot of those recalls, around the 2010, 11 sort of time, a lot of the problem came down to sheer complexity of the system, as far as they could determine. So when they looked at this in more depth, they worked out that actually to get that level of confidence that one should have in those systems to make sure they were safe, it would have taken something in the region of 10 to the power of 8 hours of testing to do that thoroughly in the vehicle operation phase. And that's really where they were looking to do the testing. So it's just an astronomical amount of time to be able to do what they needed to do to the right level. If you look at the latest QNX kernel, which is used for many embedded systems, as sort of a higher level embedded systems, but it's become quite common in things again like automotive and any medical systems and so on. It's known to have something in the region of 10 to the power of 300 different potential states, just because of the number of decisions and inputs and so on that are available in that system. It's such a massive number, we can't even comprehend that in reality as to how we're going to go about testing all of those possible combinations. We can't, it's just not realistic. If you contrast that, for example, to the number of atoms in the entire observable universe, which is estimated to be in the range of 10 to the 78, 10 to the 82, you can understand that this is really a phenomenal problem space that we have to deal with. And our traditional approaches perhaps to testing and verification and validation of these systems is something that we have to look at, because it's just not going to scale to those levels that we're going to need in the future, and even now. But standards are still important, and the testing and the verification and validation of systems is critical for our confidence and assurance to be able to feel safe in using those systems and connect our systems to the outside world. And standards improve that confidence. They give us a clear way to benchmark and measure the systems against an expected norm or against other systems of different levels, perhaps in respect to their relative safety requirements. And it gives us some independence and of that level of attainment, some independent assessment. So this is really important, and it's even more important when we're talking about systems that are developing rapidly and growing in size and complexity as the systems we're talking about now in the embedded space. Unfortunately, it all comes at a cost. And if you look at some of the research done from the aviation industry, which has obviously been a strong proponent in safety critical systems for many years and safety critical software development, they found that in some cases for the highest levels of those safety standards for aviation, we can be talking as much as $100 per line of code that goes into those systems, which, okay, maybe that's something we can swallow if we're talking a couple of thousands of lines of code for a very expensive item. It's not going to work in the kind of volumes and size of systems that we're talking about in automotive or rail systems of the future. And so, again, we have to find a way to be able to reach those levels of confidence, but at an acceptable level of cost.
You look at the size, complexity, and cost of standards, and then you really have to mix it in with, time to market. It's a function of how complex development and delivery through a supply chain is. You have globally distributed teams with many pieces of connected software, new IP, legacy code, various open source software. You're working with many different vendors. It all ends up resulting in millions of lines of code. That code is put on embedded chips. Those chips are installed in devices. The cost to resolve defects becomes exponentially more expensive throughout that entire life cycle. And really, you look at it, there's a lot to achieve. Delivering safe, secure, reliable, and high quality embedded code is a perfect storm of conflicting requirements. It's a headache, to put it simply. So what are CI/CD pipelines?
CI/CD pipelines are really the backbone of modern DevOps automation. And continuous integration, CI, continuous delivery or release automation, which we refer to as CD, they're really forming that process of steps and stages to take us from development of the software to final delivery out the door. Obviously, the CI piece, continuous integration, is focusing on the development stages of that. And then the continuous delivery, continuous deployment, or release automation, whatever you want to call it, is focusing on how we get that software then from the produced application to out the door to our customers and so on. And the continuous integration involves generally our coding phases, our version control and build and test management. And then the continuous delivery is talking about how we're going to put that together and be able to release potentially every single build of software that we produce. And that allows us to automate that process on both sides and take away anything that really is distracting the developers and the other people in the development teams away from doing their core focus work, which is making sure we're getting good quality, feature-rich code and getting that out the door quickly to our market. Continuous integration really has several key components that make it special. And we're going to focus particularly with the continuous integration piece because that's where static analysis tends to apply. And really the key cornerstones of CI are that we're trying to frequently integrate new and change code. So as our developers are working, we're trying to constantly be integrating the work they're doing, not really leaving any time for development branches to go off in their own direction and then become a headache later on, as we've all been there and experienced. Code must be managed by a code repository. We have to have that centrally controlled. And the entire process must be automated and repeatable. Again, that's the idea of trying to keep the distractions away from our developers, making sure this stuff happens in the background. We want no intervening window between the time that the developer commits the code and that we're trying to then build it. So we're trying to really make sure we're finding the issues as soon as possible with those build integration tasks. And finally, the errors are corrected immediately. So once we've found issues, we're trying to resolve them as soon as possible to make sure we're maintaining velocity and keeping our costs low. An example CI process might look something like this. We have our developers, developer 1, developer 2, committing changes that they're making to our source control system or version control system, source config management system, whatever you want to call it. That's managing the source repository. The continuous integration server in the middle top there, what it's doing is constantly checking our source repository for new changes and new commits. And upon that, it's taking those changes and pushing them through that pipeline of building, testing, and then feeding back. And that's crucial, feeding back the results of that build and test process. So was it successful or was it not? And the information then is fed back directly to the whole team, to the developers or to the management or whoever needs to know, whoever are the stakeholders in that particular point in time. And that's how the process runs. So the question is, how do the CI/CD pipelines improve our development efficiency? Stuart.
So really, the goal of CI is to really bring the issues closer to development time. Dealing with these issues earlier in your SDLC when the costs to fix are the lowest. This shift left approach provides several benefits. First, you find problems sooner and you have easier bug fixes. Identifying issues sooner makes it easier for developers to resolve build problems and fix errors when they're still in context. This helps ensure that an issue will be resolved in a timely manner and correctly. This also helps provide a build that's issue-free and working as quickly as possible. Next, you can help reduce project risk. Encouraging small modular changes to the code, you can deliver new functionality sooner. In a case that an issue comes up, CI makes it easier to back out the problems of a release more quickly. And if you want to really up your game, when you're quality gating your changes, you can effectively prevent issues from entering your main code stream in the first place. And really, all this is doing is allowing you to minimize the impact of other developers who are working locally or potentially in distributed teams. What do you also get? You get improved software quality. Maximizing the value of CI means detecting as many issues as possible in each integration build through automation. Having an automated CI pipeline can increase the breadth, depth, and repeatability of validation tests while avoiding time-consuming manual testing. And what you also get out of this is higher productivity. By automating many of these tasks, you free up your developers' time to focus on higher value feature development, keeping your velocity up. And an extra bonus to CI is it provides you the opportunity to not only automate the development processes, but a good CI pipeline allows you to use containers and hardware instances. This shift helps allow you to move to shared computing resources like cloud and cloud services like AWS, Azure, OpenStack, and others. There's no longer a need to have or use centralized computing hardware. And this also benefits disaster recovery and provides greater flexibility for command and control of your build processes. You no longer have idle machines, and there's a potential for lower capital costs by owning less fixed hardware. So how can the efficiency of CI/CD further be improved by static analysis, and how? I'll throw it over to you, Steve.
Thanks, Stuart. So first of all, what is static code analysis, or what are we talking about in terms of static code analysis in this case? Well, static code analysis, or simply static analysis, is the idea of inspecting your source code or your code base in some form and deriving some information from it without actually executing the software itself. So there's no execution or running of the code. but somehow we're deriving information from it that's going to be useful to us and to our development teams for improving that software. In this case, we're primarily talking about finding potential runtime errors, such as memory leaks, concurrency violations, and so on, which could cause system failures in the field. So this is where we're going to improve the quality and reliability of our systems. We're talking about the detection of common security vulnerabilities. So finding the things that we know in embedded systems will leave us open and vulnerable to attack. So there are many standards out there that help guide us in this route, such as CERT, CWE, DISA, STIG, and OWASP. And they're designed to find those kind of common vulnerabilities in your own code that you're writing as you're going along that could leave you exposed to those types of attacks that we hear about and hacks and so on. We can also show compliance with these static analysis tools. We can show compliance to safety-related coding standards such as MISRA or AUTOSAR, for example, which can help us show the quality of the system as far as the coding is concerned, the reliability then that would be expected to follow hand in hand with that. And we can even enforce company or project-wide coding guidelines, naming conventions, and so on, which are specific to your teams and the work that you're doing. So why is static analysis so appropriate for CI and CD pipelines? Well, we're particularly talking about CI, of course. In this case, we're talking about the development stages. But the benefit of static code analysis over other forms of validation and verification tests and so on is that it's particularly quick, because we're not going into running a whole test suite of cases and so on through our code. We're not going through that pain. It's something that we can generally run pretty easily and pretty quickly as part of that commit process. This is especially true if we're talking about analyzing just the changes as the developers are making those. So in a good CI system, our CI service shouldn't be necessarily compiling or recompiling the entire project when there are changes. It should be compiling the changes. And the idea of differential analysis or static analysis is that we are doing the same from the static analysis point of view. We are only analyzing those changes and differences and the impacts they're having on the whole system. Essentially, adding static analysis to our pipeline, our CI pipeline, means that we're helping to further reduce our cost by detecting coding defects earlier in the cycle, as well as those other build and integration issues. So we're getting the benefits of the CI system, the CI pipelines that we've just talked about, as Stuart mentioned in the previous section, but that now applies to other issues such as the coding issues, the security vulnerabilities, and the requirements for standards compliance. There are also savings for the dynamic testing steps that may follow. Any issues that we can find prior to dynamic testing, which otherwise would have caused a change and a modification to the code, which in itself would have caused a further change to the tests, all of that is saving considerable time and, of course, effort and rework. It's also true that static analysis, because it tends to find all paths and possible paths through the system that could render a defect, whereas dynamic analysis generally has to be able to run through those paths, which is always more difficult when we're talking about the fallover cases or the impossible or difficult to reach cases through that system. And static analysis obviously finds that a lot easier. So adding static analysis to CI/CD pipelines, CI pipelines, is particularly trivial, and often people who've done this have rather been surprised by how easy it is. Essentially, all we need to do is to call the static analysis tools at the point in time that makes most sense in the build process, the build pipeline, the CI pipeline. And typically that would be something after we've performed the build itself. So after the compile and link phase, there's really no point in trying to analyze code that doesn't even compile. We may as well get that stage done first. And assuming that's successful, running the static code analysis would be a natural follow-on. We would want to generally run it before dynamic testing, again, because dynamic testing and those test cases and test suites tend to take a lot more time. We may as well find problems first with the static analysis and then go on to do the more in-depth tests perhaps later, just from a timing point of view. An example of how we'd add this perhaps within a Jenkins pipeline, we'd have a new stage perhaps as in this example here, and the steps within that would then be the the steps to perform the static analysis, which might be a full integration analysis. We might do some reporting and then add a quality gate and so on. And all of that would then be steps within this particular stage of that Jenkins pipeline. If you want to perform an efficient process, and this is where the tool we work with, Klocwork, has some particular strengths, what we'd like to be able to do is to analyze just the changes. As those developers make the commits, we would want to be able to analyze, following on from an update compile or a make, we'd want to be able to analyze the changes and the impact of those changes on the system. So again, as we saw before, what would happen is we'd commit our code, our changes into the system, into the version control system or source control system. And then our CI master would go about determining that there's something had changed, and it would initiate the job. And that might involve creation or provisioning of a machine or a container, and then performing the various stages within that pipeline. So first of all, it would be checking out the changes to that build agent, perhaps configuring the containers to the right compilers and so on, and then going off compiling the change code, and finally performing the analysis of those changes as well. And ideally, all of that should be done in a time frame that makes sense with respect to the development cycles and the feedback requirements that they would have. The delta from that analysis, the issues, if there are new issues, would then be analyzed and checked against a quality set of requirements or a security gate perhaps. And generally you would have one of several outcomes. Either there are no new issues, there's nothing new to be worried about, so everything is clean, we're good. The quality gate is passed with no further questions. Or the opposite is that we have a failure because there are new open issues that have now ended up in our code stream. We don't want that, we're going to block them. And so we automatically would potentially fail that job and return the issue to the developer for rework and recommitting. Or maybe there would be a third state in that we have some issues, but the developer has marked them as things we should be having a deviation for. We're accepting them as a deviation from the standard or the requirements we're working to. And in that case, you might want to push those to some sort of code review process so that we can either approve or reject those issues being present. And that makes a very efficient development workflow for every single change that's being committed to our code stream as each developer is making the commit. An example of how our branches may differ in terms of the types of analysis we were performing is, first of all, for the main branch, the main development stream, or whatever you want to call it, typically we would want to perform a full integration analysis. So we're now talking about the idea of having different pipelines for different developer branches or branches within our system. So for the main branch, typically we'd want to perform the full integration analysis to get the full picture, to be able to produce our compliance reports, whatever it might be, and for also to share with our wider team and our management to show where we're up to at any one point in time along that branch. By contrast, the developer branches, the feature branches or developer branches, we typically don't need that level of detail or reporting. What we care about as developers is knowing what is the current status of my branch. Have I made things worse? Am I going to make the code stream worse if I commit this code? At some point, of course, we're going to pull this together. There'll be a pull request maybe where we're merging the current main branch with the 200, 300 different developer branches that are being pulled into this version, maybe, hopefully in sequence. But at each stage, those will be pulled through and pushed into our main code base. And at that point, again, for each one of those pull requests, we'd want to be able to perform some sort of differential analysis and know what that means when it gets pushed through then to our main branch again. And finally, to clean everything up at the end of the process, we would want to then have another integration analysis maybe on the next iteration of our agile cycle, or the next night if we're running a nightly build process, just to make sure we know where we're up to at some particular time stage or release phase within our project. And so within this, generally we're talking about these two different types of analysis: an integration full analysis versus this differential analysis. And if we look at that again, the developer branch that we mentioned before, we'd be talking about something that's very, very fast, just checking the changes and just reporting those changes. And we're talking here about a pipeline that might last, in this case, seconds or minutes to do that full pipeline. So checking out, configuring container, compiling, and then running the differential analysis. By contrast, if we're talking about a baseline or integration analysis, we're probably talking something that's more in depth. It's doing more in terms of the analysis. It's doing more in terms of the compiling. You can see by contrast, in this case, our compilation is a full and clean compile and link rather than an update. Our analysis is a full static analysis of the whole branch and the full reporting. And we're then running our unit test perhaps as well in that pipeline. So something that's a little bit more in depth. And in this case, now we're talking about this taking, just over an hour to run to completion rather than several seconds. So that's the difference in the time, and it really shows the benefit of being able to do those differential analysis runs for our developer branches as commits are made. The other benefit, as Stuart mentioned, is that with a well-engineered, automated DevOps automation CI process, we can be using containers rather than project-specific machines and so on for our build servers. And that allows us some freedom because we can have shared computing resources then for entire development teams, and they're all using these containers for their specific projects to represent the build environments they need. And that allows us to be far more efficient. And typically in that case, what would happen, our developers again are committing their jobs through the CI system to the shared computing resources. And the CI system is managing what kind of container is required, what type of machine instance is required for each job, and it's setting up, provisioning those machines on the fly as we need them, but carving out parts of our shared generic cloud computing or local cloud computing resource. And again, in this case, we can see the benefit of the differential feedback. If we were to run the full analysis for every single commit, we'd first of all be talking about a slower feedback time for our developers to get the results, of course, but it also means we're consuming a lot more of our cloud resources. We are consuming, something that's 2 to 4 times the normal build time to do that analysis phase when we're doing a full integration analysis. By contrast, if we're talking about the differential analysis, which is all we need for our developers to know if they've made things worse or things have got better, that's only taking a matter of seconds or minutes. And so we're consuming far less of those cloud computing resources, and it's costing us less processing time. And so that again highlights the value of being able to do those different types of jobs for different pipelines. So in summary, what we've seen is that, first of all, embedded systems are generally becoming much larger, more complex. The development process itself is becoming more complex. We're trying to involve open source and COTS and so on that's coming into our products. We're trying to meet timescales and budgets that are already predefined by the market that we're trying to work in, but we still have to meet the safety requirements, the security requirements, and the quality levels that are demanded of those products and of our company. Something must give. Something somewhere can't continue at that rate. And so what we need to do ideally is to find better ways and more efficient ways to work. Now, some of the standards are already realizing this. They're actually adapting to make it so that it's easier to be able to achieve those levels of confidence with different techniques and different solutions. But there's more we can do. And one of the things that you see is from the web technologies and the enterprise software development processes, that they have the use of DevOps automation and CI and CD pipelines has become widespread. It's been shown to bring that efficiency for our development teams. And so if we can just harness that power and maybe even extend it for the market that we're working in and with the safety and security requirements we're working to, then there are potentially very great benefits for us. And so static code analysis really should be able to enhance our CI/CD processes, our pipelines, by adding that safety and security rigor at an acceptable level of cost. We're not talking about astronomical cost now in terms of time and results. We're talking about doing that at an acceptable level of cost. But to work efficiently as possible within these pipelines, we need to make sure that developers who are trying to commit regularly and know when they've got new problems, they need to be able to run those checks with each and every commit. That's critical. That's part of the key principles of the CI mantra. So the idea of having small changes, committing often, and getting the feedback as soon as possible is something that we need to do. And so it's very important that our static analysis doesn't hinder that, doesn't slow down those pipelines. So differential analysis here, as we're offering with the Klocwork, it makes this possible. It makes it practical to do that fast feedback to developers as part of those pipelines. And of course, if we look at the cloud computing world, which is where things are slowly moving, differential analysis becomes even more valuable. And what we're talking about is less analysis time, is very simply less computation time, which means we've got less energy costs and less infrastructure requirements in terms of our cloud resources, and that means less cost. And so it becomes, in the future, this is going to become very, very clear that the quicker we can be with our analysis, the faster we can get those results for the diffs and the differential analysis, the more saving we'll have on those computing costs in the future as well. So I think that probably summarizes, where we are and where we can help potentially with static analysis and how static analysis can add on to CI/CD pipelines. There's plenty more information on our website about how to do that. So the technical details are there. But it's probably now a good time to open up the floor to a few questions if there's anything anyone would like to ask. Christina.
Yeah, great. Thanks, guys. Great presentation. So if any of our listeners have any questions about the presentation or topic, you can submit them now. We'll try to get to as many as possible. So, what sort of time do you guys think is realistic for the pre-commit pipelines?
Oh, right. Yeah, good question. So obviously it's a factor of the development process and how long it would be between commits, for example, for the developers. So if you're committing your code every hour, let's say, which is relatively frequent anyway, obviously part of CI, the idea is we want to commit frequently, so that's a good thing. But we wouldn't want those analysis jobs, the CI pipelines, to take too long. Maybe you could suffer 5 minutes in a worst case, but you'd really need to have that feedback on a sort of an hourly basis within 5 minutes, I would think. Otherwise, it would start to become quite burdensome. Similarly, we have seen some customers in the past using Klocwork that have wanted to get that feedback, or they've encouraged their developers to commit every 10 minutes or 15 minutes. So in other words, they're bringing that time right down, which is from a CI perspective is a good thing. From a static analysis point of view, it means we have to be really quite fast, because you wouldn't want to wait 5 minutes every 15 minutes to get your feedback. And so in that case, we are talking about it really needing to be a matter of seconds to get that differential analysis and the update, compile, and so on done and fed back to the developer.
Great. We have a question from one of our listeners. How can you carry out static code analysis on Android-related code?
Yeah, good question. So typically we see two things with Android. Either we're talking about extensions to the Android platform itself, and so we're talking about analyzing that code when you're sort of building Android as part of the overall system, and we commonly see that. In that case, it's quite important to be able to separate what forms the Android code base from what is the code that you're writing in addition, so that you know where the defects are coming from. And that's something we can do quite easily. You analyze the base system, and then you analyze the combined application and platform, and we can see where the issues are basically coming out of the new code versus the existing, and of course also where we're impacting with the new code on the existing system. So in other words, defects could arise from the Android code base, even though you're writing something outside of that. So a new defect could arise within that code base because of the code outside. So yeah, that's one case, and the other case is obviously with the applications themselves that sit on top of Android. And in that case, we're talking about just analyzing those separately in Java or whatever it is that sits on top of the Android platform. I hope that answered the question.
Now, when you have a build time of an hour or more, how can static code analysis be implemented?
Yes, that's a really good question. I mean, it's very important from a static analysis tool perspective that we try to make sure that the analysis times are at least somehow, well, they're certainly not going to be exponential the build time. They've got to be some sort of factor of the build time. And ideally, with Klocwork, we're talking about 2 to 3 times the build time. So if you've got a build time of 1 hour, we're talking about a worst case for a full build of 2 to 3 hours. But again, really the idea is that's for our full analysis. And what we should be trying to do is to make use of things like differential analysis wherever possible, so that we can get the feedback very, very quickly. But in a worst case, on a nightly build basis, 2 to 3 hours is acceptable. And the other key point is that we try to make sure we parallelize. So certainly with Klocwork, for example, we can parallelize up to 64 way on a single machine or machine instance. So we really can, static analysis is particularly easy to parallelize, and therefore we can be as efficient as possible in that regard. Yeah, but again, Stuart, I don't know if you wanted to add anything there.
No, I'm good. I'm trying to prioritize the questions coming in.
Questions coming in. All right, thanks, sir. So Christina, yes, hopefully that answers that one.
Great. So, you know, we have been talking a lot about the build time and the build process, but is static analysis performed earlier in the development in order to, you know, identify and resolve those issues faster?
Yeah, absolutely. Well, so again, we're trying to apply the principles of CI here, and that is that key principle that if we can find and fix early, we're saving time and money. So it's early detection and early remediation is a good thing, and that's what we're trying to do. We're trying to shift left the development team knowing about the issues, and CI is doing that for build issues and the integration of code from developers' work, and static analysis working in the same overall structure is trying to detect those issues earlier. So again, shifting left, trying to run the analysis as soon as we possibly can in the cycle, so that we can get that information and get them fixed before we have to roll things back out, or before we have to remediate later on code that's already been committed or whatever, push through to main, and that then causes problems for us. So it's really about, yeah, finding and fixing as soon as possible before we've got that code through to the main branch.
And I think the question also relates to, you know, detecting issues while the developer codes on their desktop. Klocwork supports all of it. We chose to specifically relate how static analysis can fit into your CI/CD pipeline for this talk, but you know, our Klocwork tool supports the detection early on desktop as developers code. They see issues on the fly. And then traditional, like if you were doing nightly server builds without CI/CD, we have functionality there. Klocwork exists basically anywhere that your build may occur.
Great. I'd also like to learn, you know, just a little bit more about, you know, the Klocwork product. Stuart, maybe you can answer this. I know you guys also have the Helix QAC. They both sort of do static code analysis. So what would you say is the difference between those two products?
Yeah, so Klocwork is very much an enterprise-based static analysis tool. Each has some strengths. Our focus is software security, safety, reliability, and SAST as well. We work very much in areas of you know, rapid feedback, more modern development. QAC, I would say, strengths are very much in strict compliance. Steve, do you have any more to say about that?
No, that's exactly right. So yeah, if QAC is a very strong, and it's been around for a very long time in that safety critical, very heavily compliance-based market, and it's very, very good there. Klocwork has a slightly broader appeal, and it's very much used for systems like this, where we're trying to improve productivity of the developers, where they have some level of requirement to be, you know, compliant to standards and improving general quality and general safety of the system. So yeah.
Great. And what sort of, you know, programming languages are supported by Klocwork?
We support C, C++, Java, and C#.
Great, thanks. So, you know, when it comes to containers, is Klocwork able to work on containers like Docker?
Yes, yeah, absolutely. So Klocwork is designed to run pretty much anywhere. As Stuart sort of mentioned there, it can run in many different places as developers need it to. It really is designed to fit with the existing workflows that people have. And containers is no exception. It will run there. In terms of the licensing, which is more complex around containers because each job spawns a new machine essentially as it's running through, we do have a specific package for DevOps, as we call it, which is where you're using Klocwork within a DevOps CI/CD environment.
Great, Steve. Now I know you talked a little bit about differential analysis towards the end, but just for clarification, is that just analysis of the changed files?
Yes, correct. In an ideal world, we'd want to analyze just the change files and report the defects that are relevant to those changes. But the key part here, and this is what makes it Klocwork really rather clever, is it can't do that in isolation from the rest of the system, because if we were to do that, we wouldn't understand the interactions with the other modules around those modules which are changing. So that would produce rather poor results. So what we have to do is we have to have an interaction with our Klocwork through our Klocwork server, where we sort of understand the data from the previous baselines and all of the other builds that we've done of the project, and we understand then the impact of those changes with the whole system context taken into account. So it's not analyzing those changes in isolation, but it's with respect to the rest of the system and effectively producing an update analysis of those changes superimposed onto the existing system. And that's really the clever bit that allows us to give accurate information rather quickly back to those developers.
Great. Now, do you guys suggest that static analysis is used as part of, developers' continuous integration in Jenkins?
Yes, absolutely. Yes, for Jenkins we have a plugin. That's one of the more common systems. But yes, absolutely, static analysis should be part of your developer workflow anyway. I mean, just in terms of a really efficient way to find defects, regardless of having safety or security compliance requirements. It's still a very valuable thing to have, and it fits so perfectly.
Great. How can you, integrate static code analysis then with like an IDE?
Yeah, so we have many IDE plugins for Klocwork with pretty much any popular IDE that you might use: Visual Studio, JetBrains, IDEA, Eclipse plugins, Eclipse-related plugins. Upcoming, we have C-Line and many others. Yeah. And if you don't, if we have an unsupported IDE, we actually have a standalone desktop tool that you can run in parallel to your other IDE and get issues there live as they occur.
Now, do you guys have any recommended configuration for AWS machines running these CI jobs with static analysis?
Yeah, another great question. So again, it does depend on the kind of development team size, the complexity and size of the code base we're working with, and just how quickly you want those to come back, how much resources is available. So there's a lot of constraints and so on in there, but typically because static analysis can parallelize so well, it works particularly well within AWS if you're using, say, an X large, which is a 4-core machine, I think, or 2X large, which is the 8-core machine. We can work particularly efficiently there. Because we can then split the changes across, the changed analysis across those 4 cores or whatever. But any more than that, I would probably argue that the changes were too big anyway. So we should be committing more frequently and committing smaller changes. And so that would be probably the ideal sort of machine configurations that you would be using.
Great. And maybe we could just go back over what static code analysis means. Someone asked if it means code review or execution of code also.
Yeah, so in terms of code review, we think of it sometimes as assisted code review, because what it's actually doing is the machine's going through and finding the potential problems for you to review. So in some regard, you could say that it is an assisted code review. It's certainly not the latter, though. It's certainly not running the application itself. Static analysis is about not running the application. That's dynamic.
Great, guys. I believe that is all the time we're going to have for questions today. But before we go, I just want to quickly throw it back to you both for one final thought or key takeaway to leave our listeners with today.
Well, I would say that in general, CI/CD brings a great number of benefits for developer efficiency, which is important given the problem space that we're facing at the moment. And adding static analysis to that is a relatively trivial but very efficient and very valuable thing to do for improving the quality, security, and reliability of the code that you're producing.
Yeah, and on top of that, I mean, the cost savings in terms of developing that code with being able to check it for your various standards, the code reviews, you know, shifting left where it's the cheapest to resolve these issues, and things like saving on capital hardware costs by, you know, leveraging CI and containers and cloud computing. It all becomes this really nice thing for developers and the business itself in terms of budgetary needs and time to market.
Great. Well, thank you guys again for a great presentation. That was Stuart Foster, Product Manager of Klocwork at Perforce Software, and Steve Howard, SCA Specialist and Technical Services Lead at Perforce. And I'd also like to thank Perforce for sponsoring today's webinar, as well as the attendees for joining us today. Until next time, I'm Christina Cardoza.